So today we're going to look at factoring polynomials. And I have an example of 4p squared plus 7p plus 3. And I'm going to start out by modeling it with our mat and algebra tiles. So if I had that polynomial, 4p squared plus 7p plus 3, I could use algebra tiles to model it. So let's get the parts first. 4p squared means I need 4 big squares that are positive. So I'm going to grab 1, 2, 3, 4. I'm going to need those. I'm going to need 7 p's. And p's are just like x's, and positive x's would be these green guys. 1, 2, 3, 4, 5, 6, 7. 7 of those. And then 3 just ones. So those are the little unit squares. Now the trick to factoring with algebra tiles is you have to make a rectangle. Because a rectangle's area is found by the product of its length by its width. So earlier we learned how to multiply length by width, or binomials and trinomials, using an area model and using the algebra tiles and a mat. Today we're going to work in reverse. We're going to make a rectangle, and by making that rectangle we can find its length and width. So if we use these tiles up here, what we have to do is try to fit them in the mat in a way that makes a rectangle. So I need to use my algebra tiles to make a rectangle inside of the mat. So I need 4p squared. That's for the big squared x by x's, or p by p's. So I need 4 of these. And so far that's a rectangle. It's actually a square, but it's a rectangle. And I need to fit 7 x's or 7 p's in there. So I might go something like this. 2 there, 2 there. And that's still a rectangle so far, but I need 3 more. So if I put 1, 2, and then I have 3, it's not going to work. So maybe I'll try putting some down here to complete the rectangle. And there's 2, 4, 6, and I still need 1 more and it won't fit there. So by a little bit of trial and error, I figure out that I can't make it with a 2 by 2 with these squares here, which is no big deal. I'll just move these aside and try a different arrangement. Maybe if I stack these up with a longer, skinnier rectangle. I got my 4p squares. Now I need 7 p's. Maybe if I put 1 here and 1 here, and there's 3, 4, 5, 6, but I need 7. So if I grab another one and I put it over here, get rid of those guys. Okay, and then I'm going to need some 3 1s for this part right here. So if I put a little yellow square here, here, and here, now you can see that's a perfect rectangle. And so the challenge is, first of all, to make the rectangle. Sometimes you got to move it around and use some trial and error with your algebra tiles. Then once I have the rectangle, I know this big rectangle, the stuff inside is called the area. And I find the area by length times width. So if I know the area, I can work backwards to find the length and width. So this distance here is 1x, or 1p in this case. So it looks like this, and so is that one. So is that one, and so is that one. So I have 4 of those along this line. So one factor has 4 p's, but it also has this distance. And this distance, let me scoot these over just a tad, in case that's confusing anybody. Okay, so this distance here is 1. So I would need 1, 1, and 1. So that makes this edge of the rectangle the length. Now I need the width. And that's going to be this length here, distance, and this distance here is another one of these. So now I can tell my length and my width, which are the 2 factors of this polynomial. This one is 1, 2, 3, 4 p plus 1, 2, 3. See, there's 3, and there's 4p. This one is 1p plus 1. So my two factors that make up that polynomial are 4p plus 3 and p plus 1. And I can use algebra tiles to factor that. And it's not the only way I can do it, but it's a way that helps you, especially when you're stuck, and it helps you understand where the idea comes from. Now, another way to do that same problem is to use a more systematic method. So what we do is we take this term, the coefficient of the squared term, and the constant, the a and the c in our form of polynomials, and we multiply them together. So 4 times 3 makes 12. And then what we're looking for are factors that make 12. So we're going to make a list of those factors. One factor would be 1 and 12, one pair of factors rather. Another one would be 2 and 6. Another one would be 3 and 4. So we list all the factors of 12. Now in this particular example, all the factors are going to be positive, because the only way to make everything up here be positive is to have all the numbers be positive. So we don't need to worry about negatives in this example. So then what I'm going to do is over here, I'm going to add these two factors together, find their sum. This will make 13, this will make 8, and this will make 7. And what we're looking for is factors that multiply to the product of the first and last terms and add to the middle term. So we're looking for something that adds to 7. We found it right here, the factors of 3 and 4. So I'm just going to circle that. Okay, and you got to remember, when we're factoring, we're looking for two things that multiply together to equal the polynomial. So you'll have two parentheses, and you'll have a plus and a plus, or a plus and a minus, or etc. And they have to multiply to this. So since this is all positive, we know that's going to be plus. You could guess and check around to find out what these numbers are. For example, you know, using FOIL, that the first two multiplied together are going to give you this term. So you know that something times something has to be 4p squared. You also know that the last two multiply to 3. So you need something times something that multiplies to 3. And the tricky part is to find that middle term. And that's why this systematic method works. So because I found factors of 3 and 4 that make 12, and they sum to 7, or the middle term, what I can do is I can rewrite the polynomial as 4p squared plus 4p plus 3p plus 3. Now all I really did there was I took the middle term, 7p, and I split it into two terms that added to 7p. 4p and 3p make 7p. And I got that from these factors right here. Now I could have put the 3p right here and the 4p over here, but I put these together on purpose for the next step. The next step is I'm going to group these two together and these two together, and I'm going to see if they have a common factor. Or in other words, I'm going to factor something out of each of these terms in the two binomials. So this one has a 4p as its greatest common factor. If I factor that out, I'm left with p plus 1. Now this one has a factor, the greatest common factor is 3, so I factor it out and I get p plus 1. Now I bring down the plus sign between them. As I look at these terms, I notice that they have a p plus 1 in common. That's going to be the greatest common factor of these two new terms. So I'm going to underline that. I'm going to factor that out of this first term. And that's going to give me a 4p multiplied by it when I factor it out. And over here, if I bring that out, I'm going to have a 3 left. And so I can add those together. You don't really need these parentheses the way I wrote them. So what I end up having is p plus 1 is one of my factors, and 4p plus 3 is my other factor. Now, remember back to the If you remember back to the algebra tiles, that was the same answer we got. 4p plus 3 was one of the lengths of the rectangle, and p plus 1 was the other. One last thing before we leave this example is I can check that using FOIL. Whenever I factor a polynomial, I want to work backwards and check it by multiplying. So I do my first two terms. P times 4p is 4p squared. P times 3 for the outside would be 3p. Inside, 1 times 4p is 4p. And finally, the last two, 1 times 3 is 3. Now, when I get that, I want to combine like terms. And I get 4p to the second plus 7p plus 3. Now, our next example has some negative numbers in it. We're not going to use the algebra tiles for this. We're just going to do it with the systematic method. So the first thing I want to do is I want to multiply this coefficient 2 times this constant. It says minus 24, which is really, if I change it to addition, a negative 24. So 2 times negative 24 gives me negative 48. And what I want to start doing is I want to make some factors that make 48. Now, because it's negative, I'm going to have a lot more factors because a positive times a negative is a negative. And so, for example, if I take negative 1 and a positive 48, that gives me negative 48. But also, a positive 1 times a negative 48 gives me a negative 48. So I got two choices there. Then, of course, I want to find the sum. This one's going to be 47, this one's going to be negative 47. Neither one of those are what I'm looking for. I'm looking for something that adds to negative 13. So I'm going to keep going. 2 times 24 gives me 48, but one of those has to be negative. So let's start with the 24 being negative. That adds to negative 22. Again, not what I'm looking for. So we'll try negative 2 times a positive 24. And that adds to a positive 22. So I had to keep going still. How about 3, or negative 3 rather, times positive 16? That makes 48. And that adds to a positive 13. How about a 3 times a negative 16? That equals negative 48, and that adds to negative 13. So at that point, I have found the one I wanted, but often you need to keep going until you've made the systematic list. We could do 4 and 12 and 6 and 8 and the negatives of one of those and so on. But I don't need to go any further at this point. So now what I would do is I would take these factors, I'm going to rewrite the problem 2k squared, and I'm going to use these factors. I've got a 3k and a negative 16k. Now 3 doesn't have much to do with 2, so I'll put the negative 16. So I'll put the negative 16k, this one, and a positive 3k here. Those two make negative 13k. And then I'll add the negative 24 to the end. Now you can see when I group those, I group these two together and these two together. I can pull a greatest common factor out of this one, which is 2k. And that leaves me with k plus negative 8 here. And then this one, I'll pull out a 3, and that leaves me with k plus negative 8 there. So I'm getting pretty close to done. So now I notice that both of these have a k plus negative 8. So one of my factors is a k plus negative 8, or k minus 8 if you'd rather. And the other one is 2k plus 3. And again, if we use FOIL to check that, you'll find that it checks out to be the same polynomial that we started with. There's 2k squared, there's 3k, there's negative 16k, and there's negative 24. Combining like terms, and I left that with subtraction this time. We get back to our original problem.